last video, we discussed horizontal asymptotes. Okay, this video we're going to discuss slant asymptotes. When the degree of the numerator is 1 higher than the degree of the denominator, you're going to have a linear slant asymptote. And the way that you find that is by doing long division. Alright, so let me grab the pen, get that ready to go. I'm sure you all remember long division. Alright, so we put the denominator on the outside, numerator on the inside, and divide. Okay, so negative 2 times negative 2 gives us 4, and then we have x to give us the x squared. So that would be 4x cubed. Okay, and then negative 10x squared, and then positive 18x. Okay, go ahead and subtract. We get 8x squared minus 14x. Okay, so negative 2 times negative 4 will give us positive 8, and then we have the x squared already. We multiply that out, we get positive 8x squared, and looks like minus 20x. And we still have that negative 7 there, so I guess I should have brought that down. And positive 36. If we subtract, we see these cancel out, and we end up with 6x here. Well, you can't multiply negative 2x squared by something to give it 6x without getting rid of one of the x's. So we would have a remainder here. Okay, but we're not going to worry about that because we don't need it. In this case, we have a slant asymptote at y equals negative 2x minus 4. That means the end behavior of h of x is going to follow along this line. Okay, so long division wasn't that bad. We have some different kind of rational functions this time. We have a radical. So we need to analyze the growth rates before we can figure this out. So we're going to determine the end behaviors. We have the limit as x approaches infinity of f of x. Okay, the top, the degree is 1. In the bottom, technically, the degree is also 1. Okay, so in this case, we would have positive on the top, positive on the bottom. We would have 4 over 3, because the square root of 9x squared would be 3x. All right, and let's see if that changes. We have the limit as x approaches negative infinity of f of x. The top would be negative. The bottom would be positive if you put it in just as is. So we have negative 4/3. So in this case, we have horizontal asymptotes at y equals 4/3 and y equals negative 4/3. Okay, in the next example, we're going to do a similar idea. Okay, the limit as x approaches infinity of g of x. In the top, we have a degree of 3. In the bottom, we technically have a degree of 3. As we put a positive infinity in there, we're going to end up with negative 2 over square root of 11. Okay, as we try the other side, check the other end behavior. Limit as x approaches negative infinity of g of x. In the top, if we put in a big negative number, we're actually going to get a positive. Okay, in the bottom, we're still going to get a positive because that negative infinity to the 6th power is positive. So we have horizontal asymptotes at y equals negative 2 over square root of 11 and y equals 2 over square root of 11. Okay, and the last one in this example, we have the limit of as x approaches infinity of k of x. Now in this case, the degree in the numerator is 2, and the degree in the denominator is 3. It's higher. Okay, so remember, when the degree in the denominator is higher, it approaches 0. We have a similar case when we put in negative infinity. 0. So that means in this case we have a horizontal asymptote at y equals 0. All right, so on to some bonus problems. A lot of people forget this later in the year, but it's very important. These are growth rates in an increasing order. A constant is something that doesn't grow, it just stays constant. Okay, a log, it grows, but it's like super, super slow. It takes forever for it to get higher. Okay, and on, like x squared, that grows pretty fast. Okay, but 2 to the x, that grows even faster. Okay, and then the king of growth there, x to the x, that's growing the fastest. So that we can use these growth rates to help us analyze limits. So for example, we have an exponential function in the denominator, okay, and we have a polynomial function in the numerator. So the exponential, even though it's only 1.01, it's still going to grow faster than the so 0. The bottom is a bigger growth rate, has a bigger growth rate than the top. Part B, the top is constant. The bottom, even though we have a cosine in there, we have that constant 5x, so the bottom is actually going to grow faster because the top isn't growing. 0. Now, these are pretty exciting, right? In the top, we have a log. Doesn't matter that it's a natural log. In the bottom, we would have something x to the 1/9. Even though that 1/9 is a small power, it's still going to grow faster than a log. 0. All right, next one. We have 100 to the x. Okay, nice exponential. That's pretty big, but we have that x to the x. Think about how fast it's going to grow. That's like 2 squared, 3 cubed, 4 to the 4th, 5 to the 5th. That's getting really big quickly. So then we have the bottom bigger, 0. Okay, same thing. Even though that's a factorial, and that's going to grow pretty quickly, the bottom grows so much faster, 0. All right, so using our deduction, we're going to assume this last one is 0. Well, let's see. The bottom is smaller than the top as a growth rate. So, in fact, this goes to infinity. Okay, 2 more examples here. Evaluate each of the following. We have a limit as x approaches infinity. All right, so let's think about this. We have 8 minus 3 to the infinity. 3 to the infinity, that's huge compared to 8. Okay, so it's like 8 minus a really big number. Okay, and then on the bottom we have 4 plus a really big number. Almost it's exactly just as big as the one on the top. Okay, so if you have a huge number, and you add $4 to it, it doesn't make that much of a difference. Okay, so these aren't as important. So we have a negative really big number over positive same big number. So in fact, this is negative 1 over 1 or just negative 1. For this last one, it's a little bit different. Be careful how you analyze this. Okay, I'd like you to do this one in your whisk. Take some time and think about it and be confident. You got it.